Everybody, I guess I'll let you guys settle in while I deal with the boring bits. So my name is Nick Spooner. I'm a PhD student in my last year here at Berkeley, and I'm going to be talking about efficient post-quantum zkSNARKs from Univariate Sumcheck. I'll explain what all of these things are. Hopefully you have some idea of what everything means apart from maybe Univariate Sumcheck. And all of this is joint work with a bunch of great people. So Eli Ben-Sasson, my advisor Alessandro Chiesa, Leo Goldberg, Tom Gurr, Dev Oja, Michael Ryabzev, Madaz Veza, and Nick Ward. So let's get started. OK, so what we're going to be talking about today is transparent zkSNARKs. This is kind of going to be our goal. And I'm going to do this kind of acronym thing that everyone does. So what is a zkSNARK? It's a zero-knowledge, succinct, non-interactive argument of knowledge. So you have a prover, you have a verifier, and the prover wants to prove to the verifier that he knows some witness W, which satisfies some circuit, so such that Y is equal to C of XW. And Y and X we're going to think of as being public information, and W is a secret. And this proof system, the way that it works, the prover is going to write down some proof and send it to the verifier, then he's going to go away. This is kind of the non-interactive part. Zero knowledge means that the proof doesn't contain any information about W. Succinct means that the size of the proof is kind of much smaller than the size of the circuit, the statement that we're trying to prove. And an argument of knowledge is something that is kind of computationally extractable. This is a way of formalizing what it means to know something. So all of these things require setup. You can prove that they require some kind of setup. And what we're going to want from our setup is that the setup is a transparent process. So it's just consists of kind of flipping random coins. This is often called the uniform random string model. It's also referred to as transparent. And in particular, there's none of this like toxic waste. There's no trapdoors that we have to throw away. So one additional thing that you might want that we're not going to kind of insist on, but is also a great property, is if the verifier is succinct. So if the time for the verifier to run is much smaller than the size of the circuit. Notice that in this kind of picture that I presented, this is not possible because the verifier has to kind of know what the circuit is, but we'll see some ways of getting around this. All right. So how do we build these things? Well, the original construction of SNARKs is due to Silvio Micali back in the 90s. He called them CS proofs. And what you get is a SNARK in the random oracle model. So it satisfies all of the properties that we described. So there's kind of a transparent setup, which is kind of picking the random oracle. There is lightweight cryptography in the sense of, obviously it's a fairly heavy assumption, but when you actually implement these things, really you're just using hash functions. And you have post-quantum security, so you can show that this scheme is actually secure in the quantum random oracle model also. So this is all great. So kind of why aren't we done? Well, what did these things come from? They come from PCPs. So there's a transformation from a PCP, which is this information theoretic proof system, to a SNARK. And PCPs are not great. So, I mean, PCPs are great, obviously, but don't want to offend anyone in the audience. But they are not great for kind of practical purposes because the best known PCPs are quite big. So this like n log to the cn doesn't look like very much, but when n is the size of your computation, this log to the cn factor is actually pretty enormous. And concretely, like we really want to have efficient constructions of these things, and there are no efficient constructions of these things. Kind of the constant in front of the n log to the cn is also enormous. And so really, it's just very hard to build these things in the real world. And if you want zero knowledge, things get even worse. So kind of if you want zero knowledge on the right, you need to start with zero knowledge on the left, and this makes things even worse. Yeah?
Do you mean kind of something lighter than AES? Or
No, I mean like symmetric key. So yeah, so I mean like lighter than elliptic curve pairings and things like this. OK. So this is a shame. So we're going to try and fix this. And what we're going to do is we're going to kind of not give up on what we had on the right because we really liked it. But we're going to change what we started from on the left. And what we start from on the left is a kind of more general information theoretic proof system called an interactive oracle proof. If you've not seen it before, it's a kind of interactive version of PCP. So you have a message. It's So the verifier can send a message, the prover can send back an oracle. The verifier can then send another message, the prover sends back an oracle, and the idea is that kind of the prover oracles can depend on the verifier messages, and then at the end, the verifier can choose to accept, can make some queries and choose to accept or reject. What is good about this thing? Well, firstly, we know of IOPs with linear proof length. So there's a paper from a couple of years ago, and then this very recent exciting work by Ron and Noga showing that actually you can get this linear proof length down to like 1 plus epsilon. It's really very cool stuff. And concretely, there are these kind of papers that showing that you can implement these things efficiently. So kind of they have some kind of demonstrated practical efficiency also. So that is wonderful. So what the message that I want you to get is that interaction in proofs means that you can obtain kind of better non-interactive arguments, right? If you allow interaction on the left, you don't actually gain any interaction on the right, but you can kind of do better. You can like have better parameters on the right.
So this transformation is something you're going to show us?
No, this transformation I'm going to just assume. Yeah, it's kind of the way that it works is kind of how you would expect. You kind of you take your Macaulay protocol and you apply Fiat Shamir and in order to reduce that. Yep.
So usually it's a problem when it's not constant round. You know, when there are more rounds.
When there are more, yes.
So don't you suffer? I mean, doesn't this suffer this problem?
Well, it depends on how many rounds you have on the left. But yes, the answer is yes. And we could show actually how you can deal with that. So if you have certain properties of this proof system on the left, like round by round soundness, then this implies that the soundness of the proof system on the right will be good. But in general, yes, if you have many, many rounds, then you're going to get kind of an exponential loss in soundness. But if your proof system on the left kind of looks all right, and I think all of the proof systems I know of that have many rounds, they kind of have this property that they play nicely with this transformation, then you actually don't lose that much.
Linear proof length, you mean linear in C, in the circuit size?
Yes, linear in the circuit size.
So you have to do something to achieve succinct and express.
Yeah, so this is so this over here is like a linear, like these things here are linear in the circuit size. When you go over here, this thing is going to be much smaller because of how the transformation works. Yes?
So when you say thing on the left, the
Yes.
thing is literally the table of answers, yes?
What I mean by thing on the left, I mean this proof system. So like we design an information theoretic proof system, we apply some transformation, we get some, we use some cryptography, some random oracles, we get like a SNARK. And so then the problem kind of becomes, how do we design good IOPs? So the goal will be efficient IOPs. And that's what I'm going to kind of spend this whole hour talking about. So before I go there, I'm going to introduce this language called rank 1 constraint systems. So probably many of you have seen it before, but I'm going to go over it anyway. So you have two parts of the input. There's a public input, which is these constraint matrices A, B, and C, which are just square matrices over some field F. And you want to see whether there exists a secret vector Z, so this is the witness, over the same field, such that AZ times BZ equals CZ, where this times here is the Hadamard product, element-wise product. So firstly, this thing is NP-complete because you can reduce arithmetic circuits out to it. And in particular, this is a kind of very efficient like linear size reduction, so that's great. It's kind of better for our purposes than just straight up arithmetic circuits because it has this nice linear algebraic structure that we'll kind of use a lot. It's a candidate for standardization. So there's this like zk proof standardization effort, and one of the candidates for the representation of statements is rank 1 constraint systems. And it's also been like used in some implementations. I'm sure this list is longer now than when I compiled the slide, but it's people are actually using this thing and building constraint systems.
What is rank 1?
So rank 1 kind of means this like there's just one vector here. Yeah, I didn't invent the name. I don't know when. Yes.
Linear, you mean that the matrices are sparse or something?
When did I say linear? Like, oh yeah, so, okay, so I'm gonna mean linear in the number of non-zero entries in the matrix, yeah. So if the matrices are sparse, then I should be paying linear, and I should be paying like linear in the dimension, yeah. Okay. All right, so I'm gonna talk about 3 IOPs for rank 1 constraint systems. I'm going to kind of go over the first one in a lot of detail, and the second one in less detail, and this one, which is from last week, in very little detail. And firstly, I'm going to kind of get out of the way all of the things that are the same for all of them. So they all have the same proof length. This is these like oracles. How long are the oracles? If you add them all up, they're linear in the size of the input. Note here that everything is measured in field elements, so we're kind of in this algebraic setting.
What's the size of the input? Is it the
sorry, so I should say. So I'm thinking of n as the kind of number of constraints. And yeah, so n here is really the sparsity of is like the number of non-zero entries in the matrix. And in most instances that we think about this, like the number of non-zero entries in the matrix is like linear in the dimension. So
these as n by n matrices
with like roughly n non-zero entries. Yeah, exactly. Yes. So the proof length is linear in kind of this in the sparsity. These are the things that so the things on the left. So what kind of when you do this compilation, it kind of doesn't matter too much what this proof length is. You're going to end up with like you take a log of it anyway. But it's kind of nice to know that on the left we get something that's optimal. The query complexity in each case is a constant. And the prover time is not quite optimal. It's n log n, so kind of what's going on in every case is that you're doing FFTs over a domain of size, order of n. So this is what's the same with all of these things, and now how do we write 3 papers about them? Well, they have some important differences. So the original paper, Aurora, is a paper for kind of general R1CS instances. So it supports, so these like A, B, and C, these are kind of the definition of the instance, and so this kind of tells you like what kind of instance you have. And the time to verify in this case is order of n. So this is pretty long, right? So it's kind of not very useful for any kind of delegation or anything like that, but it's also sort of optimal in the sense that if I give you matrices with n non-zero entries, you kind of have to look at them and you have to spend time n to look at them. So this is kind of the best that we can do in the most general case. But now suppose that you have some structure on your matrices. So suppose that they are succinctly represented. In particular, there's a representation, which I'll talk about later, which is of size logarithmic in the dimension of the matrix. Then we show that you can reduce the verification time down to logarithmic. You can take advantage of this particular kind of succinctness. And most recently, we kind of, so it looks like this is strictly better than this, but it also looks like this is impossible. So what we get is we get a system that achieves succinct verification for all matrices, with the important caveat that this is in the holographic setting. So what this means is that I am allowed to kind of take A, B, and C, and I'm allowed to encode them in any way that I like, and then write them down, and then like the verifier is allowed to look at the encodings during the protocol, right? So kind of this is this like holographic, like error correcting encoding of the input. And Alessandro is going to talk about this this afternoon in some more detail, but it allows you to kind of reduce the running time of the verifier.
Holographic, you mean specifically low-degree extensions, or what do you mean?
So I mean, in this case, it's going to be low-degree extensions. In general, holographic like doesn't really pay attention. Like the definition of holographic doesn't really pay attention to what the encoding is. Well, okay, we define it, I guess. I don't know if there was a definition before actually in this. I guess.
In any case, you get the input in an encoded form.
Yes, exactly. So this is also kind of when you're in the setting, you care about actually how long it takes you to put the input in encoded form, and we'll talk a little bit about that later. Benedict.
What's the difference between holographic and preprocessing, or is it?
So holographic is a notion in the interactive oracle proofs in this information theoretic setting, where you're sorry? Exactly. So when you take and I will explain this later, when you take a holographic proof and apply this transformation, you can obtain a preprocessing proof. But holographic here, I mean you have actually access to this encoded instance. Okay. Also important to note is that the query complexity, kind of the best you can get, is asymptotically O of 1, but this is using a low degree test, which is not very efficient concretely. And so if you want a concretely efficient low degree test, actually your query complexity goes up, but your efficiency improves. Okay. So, yep.
How large is the constant in the proof size?
How large is the constant in the proof size?
5 or 100? Or
it's something like 5 or 10 or something like that. Yeah, it's not big. Yep.
How big is the field?
How big is the field? The field has to be at least n. So this is really, I should have said, sorry, this is all over large fields.
Now the n log n bits.
Yeah, exactly. So if you're starting with a problem that's not over a large field, then you have to pay to kind of make it be over this large field. Yeah, so this is a weakness of all of these things, kind of which comes from the Reed-Solomon code.
An arithmetic circuit for free over the same field, right?
Yes, yes. So if your computation is natively over this huge field, then you're not paying anything extra. Yeah. Okay. So now I'm going to talk about how you build all of these things, and they have kind of a lot in common. So I'm just going to go into the basic structure, and then I'm going to tell you how you kind of build each of these on top of this basic structure. Okay, how am I doing? Great. So here you have, so I'm going to write down the R1CS problem again, but in kind of a more broken down form. It'll seem a bit silly at first, but I promise you that it makes sense. So now I'm introducing, in addition to Z, I'm introducing these kind of 3 vectors A, B, and C. And what I want is that kind of all of these 4 conditions hold. So A times Z is equal to A, B times Z equal to B, C times Z equal to C, and then the element-wise product of A and B is C. So if you take a moment, you should be able to see that this is kind of equisatisfiable with the original R1CS instance. But now we have this kind of nice structure that we can use. So we've kind of broken this down into uniform parts. So these 3 we call Lincheck because they're testing just a linear relation. And this one is called Rocheck because it's a kind of about element-wise property. And so what you could do, you could design a proof system where kind of the prover sends Z and A and B and C to the verifier, and he checks all of these things. Right? This is an NP proof system, and it's actually less good than the very stupid proof system we started with. But what you can do essentially is you can take this, you can encode these messages in using the Reed-Solomon code, and then this will give you the foundation for building all of the proof systems I talked about. So I'm going to talk briefly about the Reed-Solomon code, just so that we are all on the same page with what I mean. So the Reed-Solomon code is a code over a finite field F. What you do is you choose some interpolating set H of size n, where n is kind of the size of the constraint system that you have. And then if I take any vector, I can look at it as a vector over kind of f to the h, so indices in h. Then I can interpolate this unique polynomial of degree less than the size of h, such that it agrees with the vector v on everything in h. Okay. And then the encoding of v is the evaluation over some other set L, which in general will be somewhat larger, and in particular doesn't actually have to intersect h, it can be anywhere. And if I set the size of L to be right, it's like roughly theta of h, then this code has good distance and good rate. In fact, it achieves optimal distance and rate. And it has a couple of additional nice properties. Firstly, we have pretty efficient encoding, like n log n encoding using the FFT, so long as these domains are kind of nice. And very usefully for us, it has the multiplicative property. So if I take 2 Reed-Solomon code words, I multiply them together, I get a code word that represents the element-wise multiplication of these 2 words. So that's the Reed-Solomon code. So what happens when I kind of apply this to the R1CS problem? So now I have this like encoded version of the R1CS problem, or the like broken down one that I talked about. So now we have this set H, which is kind of my interpolating set. And I have matrices which are now over H cross H. And now I've replaced kind of my vectors with univariate polynomials. So what happens to each of these constraints? Well, so this one here, AZ equals A, becomes kind of A times the restriction of FZ to H is equal to the restriction of FA to H, right? This is really just the same as this thing, just written in a form that makes sense for these polynomials, and the same for B and C. And then this element-wise constraint becomes kind of, for every H in H, this product is equal to FC. And this thing here is kind of weird. When we check it, we're making use of this multiplication property of Reed-Solomon codes. All right. So what might your proof system look like? Well, you kind of write down FZ, FA, FB, and FC. You send them all to the verifier. And then we do something to check all of these things. Yeah.
So for FC, aren't you defining it to be the product also outside of H?
Sorry, for which one?
For F sub C?
F sub C?
Are you defining it to be the product of these two polynomials?
Oh, no, it doesn't. It only needs to be so like FC only needs to like agree with the polynomials on, agree with the product on H. It is not the product of the two polynomials, but you can kind of check this using kind of standard agreement testing type things. Yeah. So I'm actually not going to talk about how you do this. This is reasonably well known in the kind of probabilistic checking literature. I am going to talk about how you do this. So this is kind of new to our work.
So I understand the F sub A, B, C, but what's F sub C?
So F sub Z is the representation of like the input, the secret input, right? So it's like the satisfying assignment I encoded using the Reed-Solomon code, and I send it to you. Yeah. So notice actually I haven't talked about zero knowledge at all. I promise you that all of these things can be done in zero knowledge. I'm just not going to mention it.
Sorry, can I just
Yeah.
repeat? So FC is just the logic, the encoding of the thing that agrees with the product of FA and FB on H, and outside of it, it's just a sort of unique polynomial of whatever degree you want.
Right, exactly. So I guess
Point. I mean, it's not that it's going to be, the equality isn't going to hold outside.
no, it's not an equality of polynomials. But what I can do, I can actually tell you how you do it. Basically, what you do is you say I take FA times FB minus FC, right? This is a polynomial which is 0 on H, and then I check that it's divisible by the polynomial which is 0 on the vanishing polynomial on H. And this is something that we know how to do. Yeah. So importantly, this is not a polynomial identity. Okay. All right, so let's talk about, oh, sorry, yes.
When you mean FA, it's F small a or F capital A?
Oh, I'm sorry, yeah, this should be F capital A, F capital B, F capital C. Yeah, sorry. Yes. Okay, so,
It's the encoding of...
It's the encoding of, yeah, sorry, okay, so it is the encoding of little a. But I called them here F capital A, F capital B, F capital C, and so you should consider the F capital C and F little c to be the same as on. Yes, but they are actually the encodings of little a, little b, and little c. Yeah. Okay. All right. So let's talk about checking linear relations. So I'm going to move back again to kind of the standard like vector setting. So there are no encodings right now. So let's say that I'm given x and y, which are just vectors in a matrix, and I want to check that x equals my. Obviously, this is something I can do just by kind of multiplying. But because we're doing proof systems, we're going to do this in a very strange way that makes sense for proof systems. So what I'm going to do is I'm going to take a vector of linearly independent polynomials in one variable. And then if x is not equal to my, then the inner product of u and x minus my is not a zero polynomial. Right? This is by the linear independence of u. And this means that if I evaluate it at some point alpha, then in the field, then I'm going to get something that's non-zero with high probability. So
The small bias set.
yeah, exactly. But I mean, yes. So I just I take this to be any So in particular, I can take this to be like 1, x squared, etc. We actually won't do that. We'll take it to be some other linearly independent set, but it's the same principle. Yeah. OK. So what I'm going to do now is I'm going to do a little bit of the kind of shuffling this expression around. So firstly, I can kind of move the alpha inside, and I can evaluate u at like every entry of u at alpha. This doesn't change the value of this expression. Then I will use the like linear bilinearity of the inner product and split this up. And then here we're going to use the adjoint properties. So I just move this m over to the other side. It gets a transpose. Yes?
U, and how are you able to take its inner product with, like, well, how are you representing U?
So U is a vector of polynomials. It's like a, you know, it's like U1, U2, U3, etc., right? And each one of these is a polynomial. And so I can take its inner product just, you know, as a inner product over there.
That's the end.
Sorry?
Maybe I'm misunderstanding.
Oh, sorry. Yeah, this should be an n. I'm sorry. Yes. Yes, you're right. So this is actually up to n. Yeah. So this is an fx to the n. Yes. The dimensions don't match, but they should. All right. Does that answer your question? Mostly. All right. I'll settle for mostly. OK, so now we're going to do away with these troublesome n's and k's and things, and we're going to move to our friend capital H, and we're going to look at the encoded setting. So now I'm given polynomials f and g, and I want to check that kind of f restricted to h is equal to m times g restricted to h. So what does this kind of look like as a proof system? Well, I have my prover and my verifier, and they both have access to this f, these polynomials f and g somehow. So once again, I'm going to take u to be a vector of linear independent polynomials, but now it's just indexed over h. Right? Same vector, but indexed over h. And I want to check this this inner product, this like pair of inner products. So clearly, the first thing that I should do is I should send alpha, right? So I'm going to pick this alpha at random. I'm going to send it to the prover. But then it's kind of not clear, right? So how do I test this this equation? So let's kind of unpack it. First, I'm going to write out the inner product as a sum of products. So what we get is this like the sum over h and h of these two sums of these two products. So here, this is like the hth entry of U alpha, and this is the hth entry. And here, what I've done is I've kind of done the multiplication by the matrix first, and then you take the hth entry. Yeah.
I'm trying to type match. So a matrix times a polynomial, does that give you one like m times g, is that one polynomial?
So this, so m transpose U is a vector.
You want to check that f restricted to h.
Oh, this thing? So this is the evaluation. Yeah. So I think this is an h vector, yeah, like a.
M times g, is that a polynomial?
Oh, sorry. You should think of this as a like m times like g h, like that. So the bracketing is this way. So it's not mg restricted to h, it's m times g restricted to h. Yeah.
Great.
Okay. Yeah. Thank you. Okay. Then, all right, so where was I? Yes, so this thing becomes, basically I take this m transpose u, I can like take the m transpose times u first, and then do the evaluation. These things commute. And then I look at its value on, its kind of hth entry in this vector, and then multiply by g of h. Does this, any questions about this, what I've done here? Yeah.
Could you remind why f should be secret?
Why should f be secret? So f in the protocol is going to be like a time is going to be the like a matrix times the secret input. And so if I have a matrix times the secret input, this tells me the secret input. And so it needs to be secret also. Is that a question? No. All right. So now I have this, and this, you know, now I've just kind of made this expression look more complicated. So what I'm going to do next is make it look kind of even more complicated, and I'm going to replace these U and M transpose U with their low degree extensions. So now I have these vectors, which are vectors of polynomials. They're vectors of polynomials in X. I can linearly extend them in another variable Y. I end up with a bivariate polynomial. So this bivariate polynomial is the low degree extension over Y of this vector U. And this bivariate polynomial is the low degree extension of Y of M transpose U. Good so far? All right. So what this does with this equation is I can just replace this with this U alpha sub H with U alpha comma H, and M transpose U alpha sub H with UM, where UM is this low degree extension of alpha comma H. Any questions about this?
Can you clarify what you mean by low degree extension sub Y of U?
Yes. So it's the kind of the bivariate polynomial where if I plug in, so here I have kind of U in Fx to the H, right? And so U, like this polynomial U of say X comma H for H and H, right? This should be equal to kind of U sub H. This polynomial, this should be a polynomial identity, yeah. And the same thing for this M transpose U. All right. Okay. Then we have this expression, and you notice that what we're doing once we fix alpha is this is a sum of a univariate polynomial over some set H. And the question is, how do we check the sum of a univariate polynomial? Well, you might want to design something called Univariate Sumcheck, possibly. And I'm going to explain kind of how you do this. So let's kind of look at the problem in a general setting. So you're given oracle access to a low degree polynomial f, and you want to check whether the sum over the set H of f is equal to 0. Okay, so this will allow us to solve the problem on the previous slide.
And it's guaranteed to be a polynomial.
For now, it's guaranteed to be a polynomial. Yes. Obviously, in the real protocol, it won't be, but you will use low degree testing to deal with that. Okay. So the problem is, if we don't have any help from the prover, you definitely need H queries unless the degree of f is really, really small. And if we try, our usual approach, which is this Sumcheck protocol from the 90s, this gets us nowhere because it's for multivariate polynomials, right? In the first round of this protocol, you would just send the whole of f, and you would get nowhere. Yeah.
So in the multivariate case, there's kind of this connection between Sumcheck and zero checking, which is what you're kind of trying to do. Sorry, what you're not trying to do. So there's a connection between Sumcheck and zero checking, and for univariate, we do know how to do the zero checking.
Yes.
Can you kind of reverse the connection back?
You mean, can you, because zero checking imply, not that I know of, so you can definitely do this same reduction from zero checking to, from zero checking to Sumcheck, but the other direction I don't know. Okay, so what we're going to do is we're going to reduce this problem to low degree testing, which is a problem that we do know how to solve. Okay, so this is kind of the most technical slides of the talk. So once you get through these, it's clear sailing. So let's take H to be a multiplicative subgroup of the field. Okay, so we need some structure on H because kind of otherwise it's not clear how you get a handle on what this sum is. And we're going to take G to be a polynomial of degree less than the size of H. So this is kind of a special case, and then I'll show how to generalize it to remove this degree restriction. So the lemma says that this says that the sum of G of A is 0, so for A and H, if and only if X divides G of X as a polynomial. Okay. And so what does this mean? Kind of if you expand X divides G of X, you get that there exists some G prime such that G of X is identical to G prime of X times X, and the degree of G prime is kind of less than the degree of G by 1. You can also get something similar for additive subgroups of F, but the multiplicative subgroup case is kind of easier to explain, and I can actually do the proof on this slide. So let's say that the size of h is n, and omega is an nth root of unity in f. This means that it generates h. Then this sum, so I'm going to look at just a single monomial, and then we can kind of use linearity to get the sum for g. So the sum of x to the I over a and h, I can rewrite this using the fact that omega generates h to this sum. So I just put omega to the j in place of a. And then I just swap the exponents. And what I have is a sum of roots of unity. So each of these omega to the I is some root of unity. And in particular, if I is equal to 0, then this is just 1. It's trivial root of unity, and so its sum is n. And otherwise, it's a sum of non-trivial roots of unity, and they all cancel out. So if I is 0 mod n, then this sum is n, and otherwise it's just 0. Okay. So now let's see what happens when we apply this to g. So by linearity, what you get is the sum over the coefficients times the sum of over each monomial individually, and all of them vanish apart from the constant term, because everything apart from the constant is not equal to 0 mod n. And so you get n times c0. And so this means that the sum of h of g of a is equal to 0 if and only if c0 is 0, because n is not 0 in the field. Okay. And this means that x divides g of x, right? Because if there's no constant term, then everything is divisible by x. Okay. Good stuff. So how do we move now to the general case? So in the general case, the statement is a little bit more complicated looking. So now we have f being kind of a general polynomial over the field. And what we get is that the sum of f is 0 if and only if this expression holds. So there exists some polynomial h such that f minus h times the 0 polynomial on h divided by the monomial x has degree less than the size of h minus 1. And h is of kind of small degree. Okay. And how do we prove this? You basically use polynomial division to reduce to the previous case. So I divide f by zh. This gives me f, and f is identical to h times zh plus g, with the degree of g less than the size of h. And then if I look at this sum, well, I kind of expand it according to this identity. I get h of a times zh of a plus g of a. And this thing here is just 0, because the zh polynomial is 0 on h. And so this is just the sum of g, and we can use the fact that the degree of g is less than the size of h to use the lemma from the previous slide to show that g is divisible by x. And what this means is that g prime, which is this kind of f minus h times zh divided by x, right? So we kind of, we take this g and we kind of go back and we see what it is, has degree less than the size of h minus 1. Okay. Any questions about this? All right, okay. Then we're going to use this to design a protocol. So it's kind of straightforward what you do. So you just take this expression, you say, okay, what I have to do is I have to test the degree of this thing. So we both have access to f, and the prover is going to compute this decomposition, and then he's going to send me the evaluation of h, and this kind of there exists h, and then we do a low degree test. And we do a low degree test to make sure that kind of f minus h times zh over x is a degree of degree less than h minus 1, and the degree of h is the most of the degree of f. Notice that I don't need to send this thing, because the verifier is able to compute it himself just by evaluating kind of f and h and zh and x. All of these things he has access to. Okay. Any questions about univariate Sumcheck? Okay. Either that's good or I've just completely lost everybody. So, never mind. Let's just. Either way, the correct reaction is to move on. So now we're going to talk about the complexity of the verifier. So kind of, yep. Ariel.
So I'm wondering, right, so I understand this protocol where you LDT this function.
Yes.
Right, so I was assuming it was something, right, the thing I'm used to is you give h and g, or you give g implicitly,
yeah.
and then you check on a no, you give G prime actually, and then you check on a random point is F equal to H times Z plus G times
Yes,
A.
yes.
I'm wondering if those two things are equivalent, like that protocol where you give G prime and H and you check on a random point it's equal to F, and this protocol where you LDT.
So they are not equivalent, and actually doing it this way gives you kind of a better soundness error. I think they're probably the same up to some constant. Like, you know, they both give you a protocol that works. But the soundness error in this case is better because in the other case you have this kind of odd trade-off between the PIT part and the low degree test part. So formally, like when we originally came up with this protocol, it was designed like this, and then there was this kind of noticing that you don't actually need to do this this PIT actually saves you quite a lot in terms of like concrete soundness. Okay. So now that I've talked about kind of the base of the protocol, I'm going to talk about the complexity of the verifier, which is kind of a very important thing when you're actually designing these SNARKs, because the verifier's complexity in the SNARK is essentially inherited from the verifier's complexity in the IOP. Okay. So what is the verifier doing in the IOP? We're going to break them down into 3 bits. There's this reduction part, which basically takes the instance and reduces it to an instance of Sumcheck. There is the actual Sumcheck part, and then there is the low degree test. So here we use the Frey low degree test of BBHRT. The Sumcheck part is very efficient because computing these, essentially the only thing that you have to do is kind of one division in the field, and then evaluating this vanishing polynomial. And because H is structured, it's actually very easy to compute this vanishing polynomial. So this takes roughly log n time. The low degree test is also very efficient. Once again, the time is log n. And so basically all of the cost of the verifier is going to be in this reduction part. So let's look at this a little bit more closely. So here we have this vector u of linearly independent polynomials. What is the kind of reduction, what's the job of the reduction? Well, if you kind of trace through what you need from the reduction, like once you do the Sumcheck and the low degree test, basically it's evaluating this polynomial at some arbitrary alpha beta in the field. So remember that this u is like the low degree extension of this u, and this um is the low degree extension of m transpose times u. Okay, so what is the cost of this computation? So if you make a sensible choice of u, and actually this is why we don't use this powering construction, because we don't know how to do this. If you make a sensible choice of u, then you can actually compute this evaluate this bivariate extension in log h field operations. And so really the main computational task is computing this u sub m. And this is kind of a good sign, right? Because really this u sub m is the only thing in the whole computation that depends on the instance. Everything else is generic, like would apply to every instance. And so really computing u sub m should be the main computational difficulty if we're doing our job right.
Can you say a sentence about what the choice of
this thing? I can even write it down. So the answer is that this bivariate polynomial is going to be the following. Okay. So this is kind of the magic polynomial that makes everything work. Basically it looks kind of like if I take my if I take a matrix which is h by h, and I put some stuff on the diagonal, we don't have control over what's on the diagonal, but there's some stuff that's not 0, and then you put zeros everywhere else. This uxy is like the low degree extension of this thing. And so if I like take the u vector that is kind of the that this is the low degree extension of, then this gives me the properties that I want. Okay. All right. So let's talk about how you compute this u sub m. And actually, it turns out that the different ways of computing u sub m basically give you the 3 protocols that I talked about before. So let's kind of do this taxonomy. So let's just say that I naively compute U sub m just by doing Lagrange interpolation. I just work out kind of what it's supposed to be on the kind of the systematic part, and I just interpolate. This gives you basically the original Aurora protocol, so you can do this in time order of n, and it works for all matrices. On the other hand, if you notice that your M is structured so that U sub M can be computed by this algebraic tensor product that I'll talk about in a little bit, then this gives you a succinct verifier for these structured, so succinct matrices. Now, if you're willing to do some kind of like holographic encoding of the input, then you can combine this with a protocol for doing matrix arithmetization which is based on some work with, called Marlin. This will allow you to compute this bivariate LDE in time order of log n. So like once you've arithmetized this matrix, so this there is some matrix that's related to M that this is the arithmetization of, and so you get a logarithmic verifier, and you can support all matrices, but you pay the cost of kind of encoding the input at the beginning. Okay. Yes?
The verifier.
Like someone who is like, so it doesn't have to be the verifier. It just has to be someone that you trust, because yeah. In particular, you can do it once for a circuit, and then everybody can use this as long as they trust you. Okay. So, and I mean trust also not in the sense of trusted setup. Like there's nothing that kind of is, you just need to trust me to do the computation right. You could check it yourself. Okay. So in the last part of the talk, I'm going to talk about the kind of other two constructions. So firstly, I'm going to talk about the succinct construction. So like, what is succinct R1CS, right? What are these succinct matrices I've been talking about? So let's say that you have a repeated circuit, right? So your circuit basically just, you have this small component C, and your circuit is just like C, 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 C over and over again. Then when you turn it into an R1CS instance using kind of the standard reduction, if you're reasonably careful, what you get is a matrix that looks like this. It's kind of this, like it's mostly zeros apart from this thing down the middle. We call it a staircase matrix because it looks a little bit like a staircase. So this type of matrix, it turns out, is like very nice algebraically. And why is that? Well, if I divide M, which is this this representation of kind of the C and the Y's, if I divide M into M0 and M1, then what I get is this like double block diagonal matrix. So it has M0 on the diagonal, like blocks of M0 on the diagonal, and then blocks of M1 on the super diagonal. And so if I write this using tensor product notation, I get that this is the kind of identity on n, where n is the number of copies of C, times M0, plus this kind of shifted identity. So this is the matrix with just ones on the super diagonal, tensor product with M1. So roughly, this captures wiring, like M0 captures wiring inside of a block, and M1 captures wiring kind of between the blocks, right? You need this overlap in order to make these computations depend on each other. You can also bootstrap this. This is actually a very general form of matrix. You can kind of bootstrap this protocol to check RAM computations. Yes?
Is it obvious whether there should be sort of the dual of this, where the C's take independent inputs, so sort of a data parallel type setup?
That's a good question. I haven't thought about that. We can talk about that offline. Okay. So for now, we're actually going to throw out this top part and just think about matrices which have these on the block diagonal. These don't really represent interesting computations, but this is kind of easier to talk about, and the ideas that we use here can be used to check this more general form. You should note that if this looks familiar, this is kind of because it looks a bit like a quantum gate, right? Like if I have a single qubit gate, then the way that I kind of write it down as a matrix is I just tensor it with the identity on all of the other qubits. I don't know that this has any, particular ramifications, particularly because this is over a finite field, but I don't know, it's an interesting thing to know. I guess the interesting thing is that we didn't invent this kind of succinct representation of computation, right? It comes from it has a history. Okay, so what we're going to need to do is we're going to need to define our tensor product in a way that is kind of algebraically friendly. So we're going to need to like have this tensor product, and it needs to play well with all of our like low degree extensions and things like that. So let's just look briefly at how you do that. So I'm going to take my H, which is a subset of the field, and I'm going to kind of decompose it into this product H2 times H1. And then I have a map, pi1 and two maps, pi1 and pi2, and they take it to like the coordinates in this matrix, right? So it takes it to like H1, H2, where H1 is pi1 of H and H2 is pi2 of H. Okay. And this is a bijection. Okay. So now if I have these two vectors x and f to the H1 and y and f to the H2, then I can take that outer product and I get this matrix, which is the xy transpose. And then if I like use the inverse of this map to lay this out as a vector, what I get is this x tensor y. So this is kind of the map. So so far so basic linear algebra. So what is kind of interesting about this kind of object? It turns out that if we are careful about our choice of H, then we can actually make these maps, pi1 and pi2, be low-degree functions. So we can think of these maps as being polynomials, such that kind of their restriction to H has this property that it like gives you this product. And moreover, the degree is pretty low. So the degree of pi1 is the size of H2, and the degree of pi2 is the size of H1. And even better, they can be evaluated very fast. So these polynomials can be evaluated anywhere in the field in logarithmic time. Okay, this uses heavily the group structure of H. We don't know how to do this if H doesn't have group structure. Okay. What does this give us? This gives us kind of an algebraic, like low-degree extension of the tensor product, right? So I can write down this function x tensor hat y, and if I have a low-degree extension of x and a low-degree extension of y represented by x hat and y hat, then I can plug in these pi1 and pi2 things, and I can get something which is essentially a low-degree extension of x and y, of x tensor y. It is not the unique low-degree extension of x tensor y, but it's kind of good enough. So it has degree which is kind of twice as big as it needs to be, which is pretty good. And it agrees with x tensor y on this set H. So what is this bias? We can basically, the message is that you can efficiently compute some LDE of x tensor y given LDEs of x and y using this construction. Okay. So how do we use this to test these succinct linear relations? Well, what you do, you look at this kind of this matrix, and now I've kind of made it more algebraic looking. So this is the identity on H1, and M0, which is an H2 by H2 matrix. And then kind of this M here is the tensor product of these two things, where by tensor product I mean this like H1, H2 tensor product. Now, if this map here is a homomorphism, this is where we're using the group structure, then there exists these two U's, UH1 and UH2, such that this vector of linearly independent polynomials U that I want, I can realize it as the tensor product of UH1 and UH2. And moreover, I can find these bivariate extensions that I'm looking for in time log H. So what's nice about this? Well, this is compatible with kind of the tensor in M. And so what I do is I look at M transpose U. When I do this multiplication, by kind of because the multiplication distributes over the tensor product, I get UH1 in the first coordinate, right? So this this is the identity applied to the first coordinate, and then this M0 transpose is applied to the second, like part of the tensor. And this part, like M0, I'm thinking of as being small, so I can just kind of directly compute the LD. This is my like non-uniform like core. And recall that if we can compute x hat and y hat efficiently, then we can we can compute the low-degree extension of the tensor product. And this means that kind of by this equation, we can compute this U and UM in time log M.
So see, basically you wanted to get the individual degree down to square root n, and then you can do even a bivariate extension because it's time O of n instead of O n squared. That's this directly, or
no? This is not really about degrees. This is just about like you mean this thing, or so yeah. This is not.
My understanding is the high level is to get the degree down to square root n, so you can't afford to do a bivariate.
No, this actually has absolutely nothing to do with that at all. So this is just really about like we're not really doing anything with degrees or anything like that. We're just saying, okay, like I have some like u, which is a vector linear independent polynomials, and I want to compute the low-degree extension of m transpose u. And so I'm using the structure of m to say that I can do this fast. But like really in fact, maybe the best way to think about it is that from the prover's perspective, nothing has changed really. Like the prover is doing the same work in this protocol as he's doing in the Aurora protocol, except he makes a different choice of u.
Yeah, and I'm saying, why is m0t times uh2 easier than the original thing?
Oh, because it's small. Sorry, so m0 is really tiny. Like you think of m0 as being like log size. So I'm thinking of this matrix as being made up of like lots and lots of tiny blocks. So maybe this is a misleading picture because they've only got 5 of these, but you should think of it as having like a million of them. Yes, yeah, exactly, yeah. So this is okay. I see where the confusion comes from. Yeah, so this isn't to do with degrees or anything like that. This is just to do with kind of you want to make your verifier kind of linear only in the part that's like not uniform. That's not uniform. Okay. All right, so now I'm briefly going to talk about this new protocol. So this is 2 protocols, Fractal and Marlin. Fractal is an IOP, and Marlin is for something that supports kind of polynomial commitments. So this is a kind of non-post-quantum version, and this is from 2 very recent papers from kind of last week. So in the holographic setting, what you can do is you can take your matrix M and you can encode it using some error-correcting code, and then you can write it down and have the verify kind of query. So one natural thing to do is to write down the evaluation of u sub m, right? So this is kind of the polynomial that I want, and it's an encoding of m, so I could do it. The problem is that the encoding is really big, which means that the time to encode is a lot, and we care about the time to encode because it's kind of a cost that we have to pay in the proof system. If you didn't care about the time to encode, actually this would be pretty good. So the idea is that you encode m using these kind of in a sparse representation using polynomials row, col, and val, where kind of if I look at row of 1 and col of 1 and val of 1, I get like where the first entry in the matrix is, the first non-zero entry in the matrix is, and what its value is. So this is like a sparse representation of m, and this is of size kind of the number of non-zero entries of m. The problem then is kind of how do I go from this sparse encoding to this u sub m? And the answer is essentially this equation. So this equation basically gives you the low degree extension of a matrix in terms of these row, column, val polynomials. And you can show that kind of in order to compute u sub m, you need to basically compute the low degree extension of m, like modulo some reweighting. So what is this? Well, this eq sub h is the polynomial, the bivariate polynomial, where if I give it kind of a and b and h, then it's 0 if a is not b and 1 if a is equal to b. And so this says kind of I'm summing over k and k, and I want to check kind of is this the correct row? Is this the correct column? If so, then give me val. That's the basic idea. This is kind of hiding some details because this is actually a very high degree polynomial. You need to deal with that. But this is kind of basically how this protocol works, and that's kind of all I have time to say about that. All right, so thank you very much. This is all of this stuff was based on these 3 papers, 2 of which are online now, and 1 of which is going to be online very soon, I promise. And if you're interested in kind of how this all looks as like a landscape, this diagram will explain to you kind of how to check any R1CS instance you would like. Thank you.
So going back 2 slides ago where you have explained sort of if M has some kind of succinct representation as like a sum of tensors of things which are small or that we know how to evaluate at single points, then we can, evaluate the low degree extension, right? Just so you have that you can compute the low degree extensions of a tensor product efficiently. Is there some other, are there some other interesting operations that you can also, that also commutes with taking a low degree extension?
Interesting. So I mean, this it doesn't actually commute with taking a low degree extension, right? You lose something with doing this. You could take multiple tensor products. This is one kind of simple generalization. I don't know of anything else. I guess the one thing that we have thought about is kind of like we only have really 2 like matrices that we can put on the left here right now, right? We have this kind of identity and then the like shifted version of the identity. These are not very exciting matrices. Maybe there are more interesting matrices that you can kind of put on the left, and they need to be really like very structured because they're the uniform part.
I want to ask about the basic version in Aurora with linear verification time.
Yes.
So is there a repetition parameter for the low degree test?
Yes, yeah. So you can think of the linear as being multiplied by this repetition parameter.
That parameter should be bigger than say log n, right? So in practice,
I mean, it's like the security parameter, right? It's like order of the security parameter.
It's security parameter times linear.
Yes.
But if you evaluate using, for example, FFT and inverse FFT, that gives you complexity of a log n, but it's actually faster.
Right. So yes, you can. So if you're making lots of queries, then you could conceivably you could use the FFT to rather than doing Lagrange interpolation over and over again. I think there is, if you actually try and do it, there's kind of a trade-off in terms of like the number of queries where that makes sense.
But you said number of queries security parameter, which should be.
Yeah. I'm saying like in the real world. Yes. So in the like. Theoretically, I think that you're right, that kind of the right asymptotics is like n log n or something if you want to get like negligible soundness. But I think, so we actually don't do this in practice. Yeah. Any more questions? Yeah.
So, say now we go to the trusted set of non-quantum, like a Grad 16. Mm-hmm. I know my circuit is many, just even on independent copies of the same smaller circuit.
Yeah.
Is there any chance that this tensor stuff can improve something there, like a proving time or?
I don't know about proving. So like this doesn't help us with proving very much. I think there's something that you can do, but it's not. Asymptotically it doesn't help. I think that there is some. Like it has some scope to be applied to Groth 16 type things. Also, maybe bulletproofs type things. Like it seems like this is kind of a general notion of succinctness that should be applicable in any way that you want to use L1CS. But I haven't looked into it.
Okay, that's thank you.
Thank you very much.